Thank you, Holger, for that generous introduction, and thank you, everyone, for being here. And it's always a pleasant and honor to be coming to Berkeley, and always feels the energy and excitement here. Today, I wanted to have a relatively long title, kind of tell you a story that to some of you may not be very familiar, but I know at least one expert in the audience who knows quite a lot about this particular subject. I wanted to tell you, our story where we explore the roles of nuclear spin, quantum coherence, entanglement in the context of chemistry. So these are sort of physics questions, but we explore in the context of chemical reaction. So I think you'll find it very interesting. On the left-hand side is the particular system we will be digging into, where we want to ask the question of if we were to start with an entangled nuclear spin, let's say, after a chemical reaction, so these molecules perhaps entangled, the atoms in the molecules are entangled, and after the reactions, these atoms are now in two separate molecules. Can they still be entangled? That's the kind of questions that we want to answer. Well, we won't actually answer, but we will dig into these type of questions. On the right-hand side, we have another system where we have molecules prepared individually trapped using tightly focused beams, and we can also entangle, we can actually entangle them in this case where they are entangled through their long-range dipolar interaction. So these are so I'll focus a lot on the left-hand side, the story on the left-hand side, and I'll touch upon some of the highlights of results for the experimental setting on the right-hand side. Now, this year we celebrate the 100 years of quantum mechanics in the context of, in the context that I want to describe here, sort of experimental physics and chemistry. It really started, so more than 100 years ago. This is like more the experimental front where we probe the intrinsic property of an atom and molecule in isolation once molecular being, so these apparatus, which was put forward down over here, Alto Stern, utilize a molecular being, which is just really a being of molecules or atoms in vacuum, travel at its sort of natural speed. And he was able to measure velocity distribution of that being, yes, indeed, Maxwell-Boltzmann distribution. And then he, of course, everyone knows he, Stern and Gerlach's experiment demonstrated the quantized spin, the spin quantization property that we now all know, learning from quantum mechanics. Okay, so these people all have connection. They really are, trained as an atomic physicist, so they're really sort of the grandfathers of our, lineage. Stern-Gerlach experiment, and then Rabi took that, for Stern-Gerlach, these were force measurement separating the spin up from spin down. These are force measurement that has limits. Ultimately, Rabi came up with a frequency measurement to try to make that measurement much better, and that's the Rabi methods to to drive these transition on resonance. And Rabi was a postdoc of Stern, and many people, especially in the U.S., came from Rabi. For example, Ramsey, who was a student of Rabi, thinking about making that measurement even more precise, and came up with the separated oscillatory field method. And I wanted to say that as we dig into, as I was actually teaching a quantum molecular physics and chemistry course this year, and dig into the history, a lot of these measurements were done using molecules. And if you're in if you're in AMO physics, a lot of the work nowadays are in atoms, and molecules kind of like a newcomer. But actually, in the old days, molecules were the stable because For example, Stern as well as Rabi, they wanted to measure the nuclear magnetic moment really, really well. And if you have something that has a strong, if you use atom that has an electron spins, then it completely washed out, the signal from the nuclear spin, which is much, much, smaller, in terms of magnetic moment. So one has to use molecules that has an electron spin of 0, total electron spin of 0, and to really be able to probe. So really precision measurement experiment with molecule to probe these intrinsic property. Anyway, so the story goes on, and I listed here, this is more of a chemistry work where Dudley Hirschbach, who is a colleague in my department, who was a student in the classroom students of Ramsey, who decided to use molecular beam and actually in the cross-molecular beam geometry to study collisions of a single collision for chemical reaction to sort of understand the elementary process of chemical reaction. So this is briefly, looking back at the history. And of course, I'm going to be talking about molecules. I wanted to just very briefly cover the molecular quantum degrees of freedom. These are degrees of freedom that have quantized energy that we deal with, and they're covering a wide range of the electromagnetic spectrum, vibration, electronic rotation, and nuclear spin hyperfine. And these degrees of freedom can be utilized for imaging, as fingerprints to tell us what molecule it is just by looking at its transition. What I'm showing you here is an optical image of a kind of slice of brain that has tumor, which has the exactly same view, except for on the right-hand side, we had the molecular specificity, and you can see that once you had the molecular specificity, you can get a lot more information out of this. So this is an example of Raman imaging on the vibration degrees of freedom. Nuclear spin, so water, water in the copper core, which is show up here, which can be identified also with the nuclear spin. Okay, so now one more degrees of freedom, which we also often nowadays, actually get control, is the motional degrees of freedom, which you can do sort of double slit or multi-slit experiment. This is a picture from Vienna's group that you can have, something as large as vitamin that you can put through the multi-slit grading to see these kind of fringe pattern. Okay. Now, these are the degrees of freedom, and these are the degrees of freedom of molecule that were so, that covering the large electromagnetic spectrum that allows, even at the early days, even the first atomic clock was leveraged using molecule because the frequency specifically was very convenient, and that was 24 gigahertz, which is an inversion of an ammonia molecule. And of course, nowadays, motivated by better and better atomic clock, nowadays the clock precisions are way beyond what was back then, which say would not lose a second in 300 years, and now it's more like would not lose a second in over the age of the universe. So some of these techniques, okay, so here is what is the ticking of the clock. The ticking of the clocks are really just electron density oscillation in some sense, where you can see the familiar S&P orbitals, and they're in the superposition of that. There is this phase vector, and this is atomic clock oscillation, which we slow down by 10 to the 15 times, so we can see it. Nowadays clocks are, obviously going much, much faster. So a lot of the technology that was developed motivated by these, for a long time, the precision measurement front have really benefited, revolutionized our field, I would say. Starting with, the more recent ones are, for example, the invention of laser cooling for better atomic clocks. Now we have bring all those tools that was first it was molecule, and after we start to get more control, we start to work with atom and have less systematic shift, and then now we're bringing all those tools back to molecule to have more control. And already more than 20 years ago, or even 25 years ago, there was a push on getting these control on more and more complex systems, such as molecule, for a wide variety of different directions. And these pioneering papers have shown, some of the, major pillars, I would say, major directions. For example, testing, time reversal symmetry using molecule, which we now have some of the best measurement with electron-electric dipole moment search, with which of course have long tradition in this department. Now with molecules, and also ideas about using molecule for quantum computations. Of course, the spectrum of what one can do with these molecules with lots of quantum control spans from sort of single body physics search for new frontier of physics to two or many body physics, more on the exotic quantum phase of matter or quantum computation, to some new area, which is something that I want to spend a lot of time telling you about in the area of asking fundamental questions in chemistry. Okay, so in my lab, we work on sort of application scientific direction toward these sort of three areas. Okay, so let me just go into some sort of overarching question that I wanted to ask. In the chemical reactions, we have reactant that comes together to form products, and in between, there is some intermediate stage where there is a complex form, and the atom finds its partner and comes out with products. The question we want to ask is whether these products are entangled. That's obviously a very physics question, but utilizing in sort of this context of in asking questions in the context of chemical reactions. And some of the implication is if we know the answer to that, we might find interesting new application which we didn't consider before. And in context of, like in the natural environment where chemical reaction can happen, or resulting in some new technology. So these are possibilities, but very, very far away. The overarching question is to ask whether these products are entangled. Now, this is a very grand question, so it's hard to answer, and it needs to sort of take a long time, and we don't really know how to tackle them yet, but we want to break it down into some smaller questions. For example, we want to ask whether quantum phases, whether coherent, whether phase can be maintained throughout the reactions. So if we, for example, prepare something that's entangled, for example, entangled spin within each molecule, and we take advantage of that after the reaction, that molecules that contain the entangled spins are separated. Now, whether these products that, that's where these entangled spins used to, that takes, a pair, one of each pair, whether they can still be entangled. So that would be a more well-defined question that we want to be able to tackle. Okay, so in order to do that, we have a list of things that we need to follow through to be able to ultimately answer this question of whether phase, for example, phase is coherent throughout a reaction. So first, we need to be able to prepare molecule in the single quantum state, for example, in entangled state. And then we need a chemical reaction to actually break up the molecules into products, so atom exchange process. We need to detect the quantum state of the products, and we need to detect it in a way that we actually can know that this product comes from the same event, so that any unusual quantum correlation will not be averaged away, can actually tease out that quantum correlation. And it's most likely we need to avoid anything chaotic, even though chemical reaction seems very chaotic on its own, but we need to remove this chaotic dynamic to avoid, so that there is a good chance that we can see that coherence can be there, and then ultimately come up with a metric to see that whether coherence can survive the reactions. Okay, So molecule in a single quantum state, this was already achieved, as Holger has mentioned in Gila, was part of my PhD thesis, was to prepare a potassium rubidium molecule in a single hyperfine rotation, vibration, and electronic ground state. So I won't go into too much details or any details of how we do this, and you can just take it as granted that we are now able to prepare an ensemble of molecules in a single quantum state, okay? And one of the mystery actually at the time, which we later also solved, was that these molecules actually live for quite some time, on the order of seconds, that we could hold inside an optical dipole trap, isolated inside vacuum chamber, but they don't live forever. They live they live for the time scale of sort of seconds, and that's related to the two-body collisions. Okay, so that's the first thing, molecule in a single quantum state. But we didn't really know what happened to this loss. So when I started my own group at Harvard, we decided to look into what happened to them, and by building a very complicated apparatus that combines the AMO tools that prepare molecule in this very specific quantum state, or a variety of very specific quantum state that we can prepare, and with the physical chemistry tools that allow us to probe the reactions in details. And these two individuals were really the people who worked really hard to make this happen. So this is what the lab looks like a couple years ago. It's different from the usual chemistry lab and very close to an AMO lab where all the chemical reaction is happening inside a vacuum chamber where all the optics are controlling all the degrees of freedom so that we can ask this very conceptually simple questions. Okay, so these tools work as follows. We have an ensemble of molecule here. It's embedded inside vacuum with electro lenses. We can zap it with UV light to ionize it, and depends on the time of arrival, we can know the mass informations. These lenses are also arranged in such a way that we can collect the kinetic energy information. So the same kinetic energy actually map onto different radius of ring, which you can kind of see in these pictures. So this way we have two sets of information, the time of flight information and the momentum information. These, when we built it, we didn't know that we need all the tools, but it actually redundant sort of tools. I mean, these are not exactly redundant, but we didn't know. We wanted to just figure out whether a chemical reaction happened, but it turns out all of these tools turns out to play an important role in what we can actually do. Okay, so once we built the tools, we saw indeed there is a chemical reaction that happens at very low temperature of these gas that we prepare. So 2 KRB molecule would go through this complex stage where 4 atoms are together and then turns into a dimer, potassium dimer and rubidium dimer. So we were able to verify this directly by looking at the time of flight, along with some other information. So now we have molecule preparing this capability, a molecule preparing single quantum state. We have the chemical reactions. Next thing is that we need to detect the state information of the product so that we can go on to this list of things that I show you that we need to ask this question about phase coherence maintaining or not. So to detect the state of the products, we can break it up in a state selected way. So it turns out the amount of energy after the reaction is not sufficient to excite any vibration of the molecule, so it's actually a relatively thermal neutral reaction. So all the excitation can go into rotations or kinetic energy. And the rotation, so that makes the state space a little bit more narrow. And that's good for us if we want to map everything out. So we can detect the quantum state, namely the rotation states of these product molecule. We can drive an excitation, which is state sensitive, and then use a second photon to break it up. So we can target a particular state to look for molecule in this particular quantum state, and any ion that we collect by targeting that state, we say, we have found molecule in this particular state. So this is the technique. Now, in order to identify product pair that come from the single reaction event, we need to use coincident detections. So what we do is we ionize molecules in particular quantum state, potassium dimer, rubidium dimer, in particular channels, and record it on the detector and find that they need to come from the same event by constraining these events using momentum conservation. So they started out very, very cold, almost no energy collision. And after a collision, they takes away a lot of kinetic energy, relatively speaking. So they fly away with equal and opposite direction, equal and opposite momentum, basically. And therefore, the sum of there would be zero. The momentum sum is zero, is the initial momentum. And this, because we had the capability to measure the momentum information both in the XY direction and in the time axis, which is the Z direction, we can screen out events that are just accidentally the same, but not coincidentally the same. And this way, we're able to catch the state pair that correspond to a single event. And again, this is really important to tease out any quantum correlations. Okay, so with that, we have actually done, we have all the tools that we can actually map out, and we actually did this to map out all possible quantum state outcome. And this is particular looking at the rotation state pairs. And there turns out to be 57 of them, and each one is accumulating data for several days. So we did this kind of after, after we were, it's kind of 2021, so after we were allowed to be back in the lab, but with limited capacity. So the experiment sort of run 24/7 to collect data sort of without much supervision. So this was a nice robust demonstration of the robustness of the apparatus. But the key thing is that we found that these, we can compare each channel because we have these precise information. It's almost like a precision measurement where we can compare what we measure to a statistical model, which is like after they complex form and live for a long time, they have an equal probability to go to every single quantum channel, microstates. But there's degeneracy, and that's why each channel, the possibility will vary. So it matched all very well, except for 7 of them, because we can identify them carefully, which is beyond what the computational power is capable of doing right now. So that's so actually the punchline, which is sort of the most important message here. Is that the distribution is mostly statistical, indicating a chaotic dynamic for rotation in reaction. And what that means is that, as our intuition, is that these rotation degrees of freedom seems to be really scrambled very well, and therefore unlikely to see any coherence effect. Okay, so in order to avoid chaotic dynamic in the chemical reactions, we don't want to be looking at this particular degrees of freedom because it's unlikely to maintain coherence. It's not, we didn't prove that it is, but it's just like many possibilities. So it's very hard to tease out quantum correlation. And therefore, we want to actually look in the nucleus spin degrees of freedom, which is more isolated from chemical reactions. Okay, so nucleus spin in this reaction, here are the things I wanted to say. We don't actually probe the nucleus spin directly because the states are the energy difference between the nucleus spins are too close together, and then they fly away very fast, so there's a large Doppler shift. So it's impossible to actually differentiate the nucleus spin states directly doing spectroscopy. But because these reaction products are homonuclear molecules, they have to respect exchange symmetry. which means any symmetry of the nuclear spin pairs. For example, if nuclear spin is unchanged after the reaction, this one goes to, with this one pairs up. These symmetric spin will also constrain that the spin rotation, spin orbit correspondent, the orbital angle momentum or the rotation angle momentum has to be even or odd, depends on whether the nuclei are boson or fermion, okay? So by detecting the rotation states, which is something that I introduced, we had that capability, we can know the symmetry of the nuclear spin pair, even or odd, okay? So symmetry constraint when the two atoms have the same nuclear spin, K2 rotation state must be even, Rb2 rotation state must be odd. So this way we can know the symmetry information of the nuclear spins. One more thing that we could verify is that we could change the initial composition of the nuclear spin, of the reactant, and after the product that goes into, possible different states. These plots are complicated, but all it's saying is that we found that the nuclear spins are a spectator in the reaction. It's basically not involving, and therefore the population conserved. So we can predict with these combination of alpha, beta, gamma, how that would change, which changes the magnetic field, how that would change yield to the product outcome, which would change sort of exactly how we would expect it, assuming that nuclear spin population doesn't really change and participate as a spectator. Okay, so this was measured without coincident detection. So we don't quite have that quantum correlation or phase information. So now comes to the ideas. The ideas is if we want to get the phase information, we want to, in particular, even prepare entangled spins in identically prepared molecules. So this molecule is prepared exactly the same way as that one, where the molecule can have, where the nuclear spin of the atoms can be up, up, plus down, down, for example. Then can we use chemical reaction, or what happened after a chemical reaction where the atoms are exchange partners? So this red atom goes to here, this blue atom goes to there. Are they still entangled? That's the question we want to, the general question we want to ask. But of course, sorry, we can't quite answer that question, but so we try to answer an easier one, which is whether that phase information, that phase coherence can be maintained throughout the reaction. Okay, so let me analyze this. We need some observable so that we can actually measure something and then show one way or the other. So let me just write down very simply, these are assuming they're spin 1/2 for illustration. So each molecule is up, up, plus down, down. So A molecule and B molecule is up, up, plus down, down. And I'm assuming the reaction is nothing but exchange atom and keep all the phase information maintained. Then I can just multiply all the terms out, so I'll have 4 terms, and swap, potassium with rubidium, put them together. So I have up, 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 down, down, up, and down, 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 down. So what I've done is just multiplying out this equation and swap potassium with rubidium. So assuming that is our chemical reactions, all the phase information is maintained, then what we will find is, first, these will be symmetric spins. These will be symmetric spins. In the middle, I'm actually not allowed to write down that way because I shouldn't be allowed to label the atoms as A and B because they're indistinguishable. So we need to actually write it as a combined spin basis to properly symmetrize it. So it turns out there would be some interference between this channel with that channel. And in fact, how they will distribute sort of graphically is the following, where these terms will lead to symmetric, 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 anti-symmetric, anti-symmetric, symmetric, anti-symmetric, anti-symmetric, all the possibility, but 2 of them will actually be destructive interference because these are exactly opposite with that, up, down, and this is down, up. And what I can measure, again, is not the symmetry of the spin directly, but rather the evenness or the oddness of the rotation state. So that's my measurement, okay? Okay, so this may lead to something measurable. If I have an incoherent reaction, if the reaction does not keep track of phases, everything is just populations, then I actually should have all of these possibilities, but no destructive interference, because I'm just adding populations. So this leads to a measurable possibility. So let me see. Let me see that we will want to check. Okay, so in reality, our experiment will not exactly, these are not exactly spin 1/2, so they're, spin higher quantum number. So alpha, beta, gamma, which is something we can tune with the magnetic field. We work at 5 Gauss, pick a rotation state. Even is our, rotation 10 is our even channel. Rotation 9 is our odd channel for detection. If everything is fully coherent, we will expect 0 on this off diagonal, because there's a destructive interference, and there will be 0.7 and 0.3. That's just the combination of our alpha, beta, gamma. If it's fully incoherent, then we will have this outcome. And you can see that if we don't have the coincident detections, which will be like adding these two will be exactly then the same as 0.7. Adding this two will be exactly the same as 0.3. So if without any coincident detection, then coherent versus incoherent would be indistinguishable. So anyway, that's just a note. So at this point, I'm going to do a quick pause and say, how many of you think that we will get a coherent result? And how many of you would think that we will get the incoherent result? So, just a guess. So raise your hand if you think it's going to be coherent. Okay. And raise your hand if you think it's going to be incoherent. Okay. And then raise your hand if you can't decide. Okay, several of you also can't decide. Okay, so we had to, we have a simple theory, and we have, we have some quantity that we can measure. So we don't know what the nature will tell us. And the only thing is we should just check, okay? So before I show you the analyzed result, we go into all the different channels. It's difficult to see the number of counts. But it turns out there's quite a bit here, 490. Quite a bit here, but about 3 times less, 180. On the off diagonal, there's a few counts, actually 20, but it's much smaller, so it's already trending in a coherent direction. We're careful experimentalists, so we also measure background. It turns out these are more background. These are more background counts because they are from 2 photon. They are from sort of off resonant ionization. So these sort of mix up with our resonant detection. So if we subtract that in a normalized way, this is what we measure. Okay, so put them in the picture. So there are the 2 possibilities due to these incoherent versus coherent. And our data is shown in red. And you can see that with very high degrees of coherence is preserved. Okay, so this is actually, I think it's actually quite surprising. I mean, either way, you can make arguments for that you can believe one or the other. And I'll show you why. So, if in this particular case, all the people who raised their hand for coherence obviously got it right, but we wouldn't really necessarily know that without doing the experiment, right? Okay, so very quickly summarize, we did all these checks, and we checked to see coherence survive the reactions, and in this case, it did. Okay, so this implied products are entangled, but it's not yet rigorously shown, because to show something entanglement, we not only had to have correlation, we had to measure things in different bases effectively. So that's a much harder measurement to do, which we don't actually know how to do yet. So this is something we're still thinking about how to do for the future. But one might ask, Actually, this is the first point. So we map that phase information to the population measurement, even though so far we only measure population. So not a rigorous show of entangled product. So it's not that, but the phase information, the phase preserving is what we are able to show. But one might ask, those people who raised their hand on the second, guess, is the natural question is what would actually break the phase coherence? And it depends on what experiment you work on, the kind of system you work on. I think, you will have different intuition because you would think like a lot of things can be coupled into such a degree of freedom or somehow just decohere the system in such a way that it seems very unlikely that coherence will maintain. But our goal is to find out exactly what kind of mechanism can change, the outcome, can decohere the system. And is it general, what about reaction in warmer conditions or liquid conditions, for example? And how do we actually harness that reaction for quantum applications? Okay, so I would say that turns out this was not general, or at least we can change our initial state. So previously we have, in an entangled state, but an energy eigenstate by starting with molecule, at 500 Gauss, ramp the magnetic field down to 5 Gauss, where the spin-spin interaction is strong, such that we can start in an entangled state, but still an energy eigenstate. Now we can do more manipulation where we can prepare the nucleus being in an entangled state, but by populating them through microwave drive. So it's not an energy eigenstate. And when we try that, we got kind of like, not as a clear, black and white or 0 and 1 result, where, things are kind of, maybe in between, or even there may be even result where points are lying higher than what is possible when we think a statistical mixture. So there is some kind of phase information in here that one might be able to dig out, but this is just purely experimental result, and we don't really quite have the interpretation. Okay, so the question is, so what can we do? We don't have the sensitivity to measure the nucleus being on the outcome directly. We have to, utilizing the rotation state as a proxy, as a correspondent to tell the symmetry. What we can do now is actually coming up with the idea of this reaction interferometer, where we want to alter the phase of the collision going in and see how that changed the outcome. So specifically, we want to split the cloud of two K2 molecule into 2 clouds, imprint phase for one of them, and combine them back, merge this cloud back and have it collide. And our beam splitter is this reaction itself, which tests the indistinguishability of the initial states. And then these molecules, the product molecules, we will use coincidence detection to find the outcome, okay? And in this, this is the experiment we're setting up right now. And we do expect, if everything is maintained coherence, like our simple models, we will see how that phase, as we alter that phase, how that products between the different channel, EOOE, OOEE, will vary as a function of that phase. But if something is in between coherence and incoherent, then it may be a combination of this and also the fringe contrast. So to do that, we are beginning to split. This is just to show that we're beginning to split the cloud with basically a boosted optical modulator to split the cloud from 1 to 2. So stay tuned as we'll do more experiment to find out. Okay, so I have about 15 minutes or, yeah. Okay, so what I tell you about is that, we are interested to entangle physical systems. What I have explained so far is to think whether we can take advantage of chemical reaction by starting prepare entangled spins, which is relatively trivial to prepare, but leverage chemical reaction to do the separating work and while keeping the phase information maintained. This is of course ongoing. There's a lot of questions that we want to ask. But a more usual paradigm is to use a well-controlled interaction. And in this case would be dipolar interaction with molecule, which is something that we've been working on for a long time. And in this particular system is a molecule in optical tweezer array, where individual molecules are isolated from one another, so they never come close to react or touch one another. And this also leads to our realization of the I-swap quantum logic gate with molecule, which, after sort of 20 years of thinking about molecule for quantum computation, we finally have a quantum logic gate with molecules. Okay, so molecule has, as I've already shown you, the molecular degrees of freedom in the first introductory slide. These degrees of freedom can all be harnessed and also be leveraged for a wide variety of different applications that we can think of to fulfill for something that we are aiming for quantum science. Moreover, these molecules, because their charge distribution is uneven, they actually naturally give rise to dipolar interactions, okay, with some separation. So these complex but intrinsically coherent qubits, as I call them, will allow us to tailor to sort of multiple requirements in one package. And of course, the prerequisite compared to the last part of the talk is that we need to have more control. We need to have individual particle control and to control their interaction. So that's what we have been working on a different side of the lab for a long time. So there are actually sort of two general approach for programmable array of single molecule. There's a number of groups in the world are now making this. And the two approaches are, using the same approach that I was just telling you, assembling these molecule front atoms. So that's how we do for KRB molecule. But this time we actually start with individual atoms, so the end result is individual molecules. Another approach, which is pioneered in John Doyle's lab and also in Lawrence Check's lab, is laser cooling of molecules and then grab those individual molecules out of an ensemble. Okay, so we'll focus on this particular approach that gives us single particle control, single state detection capability, molecule in the low vibrational ground state, in the motional ground state, and all these degrees of freedom. The particular molecule we choose is sodium cesium as its species because it has a very large dipole moment on sort of absolute scale for molecules. Absolute scale for molecule, probably the biggest dipole one will see would be about 10 dBi, and this is about 5 dBi. Okay. Resonant so it turns out these molecules can interact even in the absence of electric field. We can just, as long as you put them in the right state, remember these S&P that I show you in the ticking of the atomic clock. These are also S&P for the molecular rotations, which are, instead of separating by electronic transition, they're separated by a microwave transition, so 3.5 gigahertz. So it was already recognized that, in the absence of laboratory polarizing electric field, one can have this flip-flop, spin exchange interaction. Dipolar exchange can be mapped onto spin exchange. And molecular, this has also been shown in molecules and Rieber atoms and magnetic atoms in other systems. In order to make a gate, we leverage also these dipolar interaction, introduce a third state such that we can switch on and off these interactions to allow any arbitrary initial states to be performed under these universal gates, and also allow them to entangle via this same dipole interaction. Okay, so there's many states for a molecule. That's the pro, but we can always pick up the right sort of states that we want, but then they're also in the background. This was actually a lot of the sort of early work was done with Jessie, who's a postdoc here in Holger's group. And she built out this whole lab and very complicated apparatus and pioneering actually making these sodium cesium molecules. Since then, we're able to continue that work to continue the control. We identify 3 levels. We call it 0, 1, and E, which are labeled over here. We can trap these molecules in optical tweezer in such a way where our polarization of the trap is at a particular ellipticity such that the trap for the 2 rotation states are identical. This is important because any intensity fluctuation will give rise to fluctuation of the energy level, and that can easily wash out the dipolar interaction. We also need to read out the states of the molecule, which is important for in a single shot to be able to get as much information as possible. Okay, so long story short, these molecules, we can tune their dipolar interaction by tuning their laboratory ellipticity, relative ellipticity orientation to their separations, which actually is tuned by the changing the wavelength. The retardance is a bit of a technical aspect. And we can show that once we prepare them in this magic trap, we can prepare superposition of them that they can interact these dipolar interaction, which you can see is quite coherent, which was nice as we expected. And if we wait the right amount of time in that preparation, this actually will create a Bell state. So this is actually an entangled state, which we can actually characterize. So let me just say, that time scale is about 600 microseconds. We can characterize the entanglement fidelity, Bell state entanglement fidelity, by measuring population and by measuring the parity correlation in some sense. So I won't go into too much detail. These are pretty standard measurements now since the introduction of the Bell state entanglement by the atomic ion community. We now use this routinely. The entanglement fidelity is 0.94, which is, we were actually quite happy about this because this kind of our very first measurement of entanglement is already breaking into the above the 90%. A year or two ago, this entanglement molecule was also done on the laser-cooled systems, where their numbers actually is also pretty good, but not quite in the 90% range. But although we were happy about this, we're also a little sad because we thought we would do even better. We thought the number will already be in the 99% because we worked very hard about molecule, and we think the intrinsic property of the molecule will already carry us really far. So the question is, why not yet? How can we do better? Well, it turns out, actually, so let me just read. The biggest suspect is that molecules are not cold enough. Even though we prepare them to be very cold, they're still not cold enough. And the challenge is we don't necessarily know immediately how to measure the temperature of these molecules because the detection of these molecules are not as straightforward. It's not like a ballistic expansion and things like that. Always have to convert back to atom. So this is a little bit out of order. So what we found kind of in a novel sense, serendipitously, is that there is actually a rotation motion coupling, when we, due to the fact that there is a bit of astigmatism in our tweezer, coupled to the fact that we have magic ellipticity, it's not so much magic once you have astigmatism And that actually leads to a displacement change depending on the states of the molecule. So if you do a pi pulse from rotation ground to rotation excited state, the wave function displays a little. And that can be measured with a combination of different sort of pulse sequence. These are sort of the pulse sequence. Details don't matter. This allows us, in collaboration with Anna Maria, Ray, and Gilla and her excellent postdoc, that we were able to leverage this spin rotation motion coupling to extract the displacement and then the temperature of our molecule. And it turns out the axial ground state was 30%, which is not bad, but is enough to explain. Actually, it's enough to explain. That's a little out of order of this animation. It's enough to explain our decoherence. So this curve here is actually a theoretical simulation given our measured temperature and the one-body decoherence to show that the main limitation of our two-body coherence is indeed this motion. Okay, so we think, like we use, at some point we have 80% ground state fraction. Now we only have 30, so obviously that can be achieved. And with that, and also fixing some aberration, these astigmatism will also lead to a little bit of contribution to decoherence of two-body in general. We have sort of a way where we can envision that we can have an infidelity go to a very high number, 2 to the 10 to the minus 4 even. Okay, so with that, I want to just, in the last slide, just say that, we know entanglement can be very good. I mean, it's already 94%, but we can do much better if the molecules are colder. But we can also do actual logic gates, whereby introducing a third level, which are these additional hyperfine level, to switch on and off these interactions by flipping in and out of this manifold, with a total gate time on the order of a millisecond. And I won't get into the detail. It turns out, the entanglement fidelity is similar. Basically, that is already characterized. But flipping in and out turns out to be much more lossy because this is more of a single body control. And that is due to the complexity of the molecule states. Number of states is very complicated, and there's lots of stark shift during the process. So really the punchline is that we're able to demonstrate quantum logic gate for molecule for the first time, leveraging the intrinsic molecular property, but quantum state preparation remains a key challenge, which is something that we continue to have to work on. Okay, so with that, let me just quickly summarize. I told you 2 experiments, mostly concentrated on asking the question about whether reaction products can be entangled, which is an overarching question. We really answered the question about whether phase can maintain coherence. And even the answer for that is it really depends on the initial states, and why that is the case, we're still trying to explore. And I have some very interesting discussion with Professor Dima Booker, and they have seen sort of hyperpolarization with para-hydrogen. These topics are all very much related, so I'd be very grateful for the discussion. On the second part, I'll very quickly show you that we have, after 10 years of efforts, we can individual molecule under control, get them, interacting and do, logic gates and things like that. Okay, so finally, I wanted to thank everybody. This is my team from last year, and many people have already moved on. They're really the ones who make these experiment work. Yeah. Thank you for your attention.
Thanks for a wonderful talk, Kang-Kuen. The session is open for questions. In the back.
Yeah, so I think there is kind of going into a couple different directions. So nuclear spin coherent can be very long. Is a very general things in a general sort of case for a lot of different systems. So one would not like this experiment being very cold may not be sort of the crucial ingredient. I don't think it's the crucial ingredients to show what we're showing here. So I think what the crucial ingredient, what we're showing here, is that we have a ways to check these quantum correlations. You know, that's really the key element. And I think it could be more general. And I think Dima may have examples. So I would be very interesting to see, although I think it may be difficult to prove, it's more convoluted to prove, you know, I think checking the phase, at least at the moment, I don't know how to do it without having to access the individual, you know, the pairs of the products to check that at the individual levels. But I think it could be general, and this temperature, just from the fact that nuclear spin is quite isolated from many other degrees of freedom.
Sorry, but just given that like many reactions usually happen a lot more elevated temperature, so if you want to make it better in that case, I mean, do we think you'll be able to utilize the sort of like bigger molecular systems or like reactions?
I think it's very hard to prove it, but it doesn't mean it doesn't exist. You know, I guess it's what is, yeah. So I think I guess that's what I would say. It's like very hard to prove it because like the way that I'm thinking of is very brute force. Like you need all these ingredients to show this quantum correlation, but in elevated temperature or in liquid you know, states, as long as they are isolated, these coherence may maintain for some time before it decoheres. Yeah, I mean, just it's very difficult to. I mean, I guess it's also difficult to disapprove it. I guess. Yeah. But I wanted to say that, you know, that we've measured everything with the rotation degrees of freedom. So even though rotation itself is chaotic, you know, I show you it's kind of chaotic. It's statistical distribution. But if I only care about even or odd, you know, not the individual distribution, they are somewhat constrained by the spins. Therefore, one imagine they're also phase coherent. So it seems like it's hard to know what I can, you know, it's like, so I guess what I'm saying is like they might also stay coherent. It's just like they go to 57 channel, you know, like, but it could be a superposition of them at some point until it becomes, you know, a population and lost phase information. So when does that happen? We also don't know. You know, we would be interesting to probe it.
Yeah, over there.
Yeah, so it's I don't have that slide now. So basically, the polarizability of the molecule in different states depends on how you polarize them. Like the polarizability, if your electric field is parallel or perpendicular to sort of the orbital shape in some sense. So the magic ellipticity kind of so in the ground state it's spherically symmetric. You know, S state has a spherical symmetric. So it's a kind of combination of all, I think 2 times the perpendicular direction or 1 times the parallel direction. And the P state, P state has this characteristic shape, but 3 of them in different directions. So the magic ellipticity kind of in a particular direction gets the right combination such that these 3 added together to be exactly sort of spherical in some sense. So that's the general intuition to use the magic ellipticity to get exactly the same magic, you know, optical potential as the ground state.
Yeah.
Hi, Professor. So, thanks for the talk. This seems kind of like one of those questions which are really obvious but no one bothered to ask. Like, this is awesome. So I was kind of curious as to like what inspired you to actually ask this question. It's like something like, oh, is chemical reactions coherent and entangled? Is like kind of a no-brainer question. It seems to have taken so long time. So what inspired you to take?
Yeah, I think it's really once we saw in this actually chemical nature chemistry paper. It was this paper where we saw nucleus spin was spectator, which we used exactly the same model, which I explained, to explain these data. But we didn't at the time have coincident detections. So then we decided we really need the coincident detection to add that capability, and just to think like once we see this, just think like it's possible. But what is the ingredient that we need to actually make it happen? And then so when we actually add the coincident detection, what we did was actually this measurement. This allowed us to actually map out the whole spectrum, whole outcome. So this was actually followed after we add this coincident detection. But what we actually didn't know is that even though we could, once we add the coincident detection, we know we can make correlation measurement, but we didn't think that it would be sufficient to get phase information until we just try and then decided in this math, like actually they would be destructive interference. So it's like a lot of the idea is like it's kind of there, but we don't know whether it'll work. And I say like, let's just try some, and then the student really try to figure out the math more deeply, and then realize there's actually a way to prove one way or the other. And then now we can sort of continue like, what is the next thing that we can do? Yeah. So it's kind of organic, I would say. Is coupled to the capability that we gain over time.
We might have time for, well, if they are short, then 2 last questions. How about in the back, and then in the front?
You mentioned that out of the 7 possible outcomes, 7 could be actual expectations. Why did those 7 actually?
We don't know. There's not a computation, explanation. Yeah. Well, actually, one of them we know because one of them, as the product comes out, it turns out there is some the relative angular momentum, and that angular momentum barrier is higher than the energy that exists in the system, so it just kind of prohibit from coming out. But all the other 6 channels we don't know because we only have these. Even though it's only 4 atoms in the system, it's too complicated to calculate exactly. So the only theory we have is to say it's just a black box. Every microchannel is treated the same way, that it's equal likely to populate, and we count the number of channels. And that's the statistical model. And there is just no sophistication in the next level calculation. So we don't really have any explanation. Yeah.
Do you want to ask the last question?
Yeah, so you mentioned that you haven't been able to confirm whether the products are entangled because you haven't been able to use basis rotations for the qubit. Why is that?
Well, so we will need to be able to measure the nucleus spin directly. That would be the most direct way. And then the nucleus spin spectroscopy would be difficult to perform because they're flying away very fast. So the Doppler shift is easily washed out the energy difference between them. We are thinking about ways, and not getting funding on that yet, thinking of a way where we want to map the nucleus spin to some electronic spin transition, so like magnifying that and then do a Stern-Gerlach after that. But these are just very general ideas of possibility, but we don't really have any concrete ideas. Yeah. So mostly like we don't know how to detect it. Yeah.
Excellent. Let's thank Kang-Kuen once more.
Thank you.